Okay, guys, let's start off. I'd like to introduce you to Dr. Julien Benoit. He's from the University of the Witwatersrand, and he's quite an amazing guy. He's into paleontology, and he's going to talk to us about the evolution of cetaceans' brains and intelligence. So, a very interesting talk. For those of you that do not understand the French language, you must listen to him. He's got a very French accent, but it's beautiful. So he will talk slowly, and if you've anything, we'll have time for questions at the end. So over to you, Dr. Julien. Thank you so much for coming. He's flown on his own cost all the way from Johannesburg. He's come here. He's staying at our guest house, and he drank about 3 bottles of wine last night because he's French. That's what they do. So hopefully it makes sense. Thanks, Julien.
Thank you very much, Lloyd. Yeah, I need to get my wine blood pressure correctly. Hello, can you hear me? Yes. Sorry, so that's my actual accent. So I've been in South Africa for 8 years, and it's still like that. So I guess at that point, there's nothing else I can say. But it's gonna stick like this forever. I'm very well aware that I'm difficult to understand sometimes. So if there is anything that I need to repeat, please do not hesitate to raise your hand, scream, throw something at my face, like a shoe, if you have a shoe, a flip-flop. I think flip-flop are softer, so it feels better on my face when I when I get to that point. Okay, so, well, intelligence, that's, I'm speaking to a crowd of whale lovers and whale enthusiasts, so I don't think I need to really convince you that whales and dolphins are intelligent animals. That's pretty acted for you. But in the scientist community, we like to think about why do we think whales and dolphins are intelligent? What are the arguments behind it? So I think it's good to remind why we do things that whales and dolphins are intelligent. And Lloyd already reminded you some of those reports that made us think that these animals are quite smart. And it's good to remind why we do think that whales and dolphins are intelligent, because it's not that easy actually to determine if an animal is intelligent or not. For a human being, you just put a couple of electrodes, you do brain imaging, and you know exactly what's happening in the brain when you do this, when you do that. Brain activity is very easy to map in a human. Now when you think about whales and you think about all the limitations that size imposes, environment imposes, because they are aquatic animals, they are not terrestrial animals, so it's much more difficult to access. Then how do you put a blue whale into a CAT scanner? It's tough enough. So you see, like just anecdotally, like nobody ever get the body mass of a whale. You just estimate the body mass of a whale. You never actually weigh a whale. So, well, at least for the big ones. So now can you imagine how you get access to the information on the brain? Question mark. So it's good to remind us why we think these animals are intelligent. And the first is they have problem-solving abilities. You give puzzles to solve to a bottlenose dolphin, and the dolphin will solve it, as long as it does not involve having an opposable thumb. Because of course we are primates, we are used to our opposable thumbs, but when we design a puzzle for dolphins, we have to design it in a way that they can actually physically solve it. Because not solving a problem that requires you to catch something with this and see the dolphin failing at that test, it's like, yeah, you know, they are not smart. They can't solve that. They can't open that bottle. Yeah, but you need to unscrew the top of the bottle. So yeah, of course they cannot open it. So, but when the puzzle is well designed, dolphins can solve those puzzles. The mirror test, very famous test to address self-awareness. Dolphins do succeed in the mirror test. So they can identify that dolphin in the mirror as themselves. And for that, you have to paint a spot on the head, and then watch their behavior as they notice that there is a spot on the head of that dolphin in front of them. And you have to monitor also the sounds that they are producing. So once again, it's extremely difficult to read the behavior of the dolphin, and that requires very, very well-designed tests. Now the social behaviors. So of course you know that dolphins and most whales are social. They live in pods or groups. And of course when you watch the sardine run, you quickly realize that even sardines live in social groups. So what's the difference with dolphins? Well, the difference with dolphins and whales is that dolphins and whales display different social behaviors, a wide variety of social behavior, and it's that variety of social behavior that tells us they are intelligent, they have social intelligence. A social intelligence that, as you can see, is compared to that of apes and even chimpanzees. So in that particular area, social intelligence, they also tick that box. Tool use, another important landmark for intelligence, and again quite primate-centered. Like we as primates understand intelligence that of other primates, and here we've seen dolphins using tools just like primates do. So here you have two pictures of dolphins. Maybe I can use that instead of using my fingers. Let's be intelligent. So here and here you have two dolphins using a sponge, and we know that they use this sponge to deter animals from the sand. So this is a good example of tool use. And here you have a seashell, and the dolphin sets a trap. So he puts the seashell in some place, chase a fish such that the fish will go in the seashell to hide away, and then catch the seashell and but you can imagine the logistics that you need to highlight a behavior like this. You need to be able to follow the dolphin, to monitor its activity for a long time before you can actually catch that behavior and certify that this is the behavior that we think it is. So that's an extremely difficult effort to get to that point. But it's very rewarding because here it's not just a tool use, it's also a trap. So it's a strategy also. So it's double the intelligence and knowledge transfer. As you've noticed, Lloyd, there is a transfer of that knowledge then from individuals to another. So they do teach each other. Communication is of course extremely important in cetaceans. So whales with their echolocation and their clicks, and dolphins with their echolocation and their clicks, and whales with their songs. So here, for example, here are some examples of whale songs, and we scientists have noticed that these songs are not just songs. They have a grammar. These are sentences, and they answer to each other. And as Lloyd presented, they answer to each other through long distance. In the case of baleen whales, it can be thousands of kilometers because they use infrasounds, and these infrasounds spread very far in the ocean. So these are extremely complex ways of communicating that not only dolphins this time, but dolphins and baleen whales do. Dolphins, for their demise, are extremely easy to train. At least the bottlenose dolphins and the killer whales are easy to train. And this is a sign of intelligence because it means that these animals can understand the language and behavior of another animal, aka human beings. They can interpret what we want them to do. And that's a big sign of intelligence. That's actually one of the landmarks of intelligence. Very few primates can go to that point when you think about it. Orangutan, for example, are extremely difficult to train gibbons are extremely difficult to train, so even some apes are very, very difficult to train. Strategies, one of my favorites. So we know that whales and dolphins are famous for using some strategies, and my preferred is the wave washing. You see 3 killer whales coordinating and swimming all together to create a wave that's gonna wash that seals off the iceberg. So you see, that's a huge accomplishment for animals that would be unintelligent. If you assume that these animals can do that without being intelligent, I don't think you're being particularly parsimonious. So now there are other behaviors that are complex and strategies that are complex. So the bubble netting, of course, the trap feeding, in which the baleen whale opens its mouth, and instead of just gulping straight, waits for the fish to come to her. So same thing, it's a sign of intelligence. She doesn't jump to the food, she waits for the food. And the lobtailing that Lloyd already talked about. So the lobtailing, where the whales flap on the surface of the water. So before talking to Lloyd, I thought it was a hunting behavior, but apparently it is not. So, but anyway, these are all transmitted from whales to whales and from dolphins to dolphins, which also testifies to a culture. They do have a culture, they do transfer knowledge to each other. And the last thing, the mourning of the dead. That's also an extremely advanced behavior, only seen in some apes and elephants, so animals that we traditionally consider intelligent. So again, it's extremely difficult to monitor in wild whales and wild dolphins because of their environment, their particular environment. But we've seen, for example, in delphinids particularly, there is a high amount of post-mortem attentive behavior. So basically, after the death, dolphins stick around for some reason, which could be mourning of the dead. And that's where I have to draw a red flag. It is one thing to say that whales and dolphins are intelligent, but we must be careful not to over-interpret the evidence. So for example, here, this was brought out by a biologist named Justin Gregg, and he's describing the behavior of an animal as their social lives are complex and they can congregate in large groups. Their heart rate increase when they notice a family member suffering. So empathy, and sorry, my English is still not good. So empathy, social life, they sound the alarm when they discover food or a potential threat, so communication, and experiments have shown they even anticipate future events. So anticipation of the future, that's another sign of intelligence. Yet that biologist was not describing a dolphin, he was describing a chicken. An animal that we traditionally do not consider very intelligent. Although you may consider the fact that there are at any time 30 billion chickens in the world, 30 billion, so they are very successful. In fact, maybe we are being exploited by chicken to feed them. Who knows? You see, it's very easy to overinterpret that signal that I gave you, those 8 points that I gave you. It's very easy to overinterpret it. So. And also, we as human beings have a trend to anthropomorphize everything we see. And I say everything because it can be people, but it can be also animals. That cat is not grumpy. This is just his face. But it's not grumpy. It's in fact a very happy and healthy cat. And that tomato is not sad. I know you think it's sad. because that's what we do. Our human brain likes to see human behaviors, human traits in things that are not human. That's what our brain does, because human is its main threat. So we are our main predator. So, and here you've probably seen, so that applies of course to behaviors, not only to animal and tomato faces. That applies to behavior, so that duck, who here thinks that this duck is feeding the fish? Of course, you know I'm tricking you now, so. So you've probably seen that on internet and shared it on Twitter or Instagram or whatever social platform, saying, oh look, this duck is feeding the fish, this is altruism, this duck is so selfless, you know. No, this duck needs its food to be wet in order to swallow it, and the fish are actually parasiting that behavior. These fish are actually taking advantage of the duck's inability to swallow dry food. So this is actually a very selfish behavior from the fish, and an unfortunate behavior from the human being who put the food on land instead of in the water. So that's what's happening. So we need to be extremely careful not to anthropomorphize animal behavior. And this is extremely difficult with whales and dolphins because they are so cute. We love them, so we need. That's why I introduced that final argument to discuss whale intelligence, and actually I'm going to spend most of my time now on this argument, which is brain size. Whales and dolphins have a large brain. We will see that right after this, and we as human beings know that having a large brain is the engine of having intelligence. So during our evolution, human hominins, as they evolved into human beings here, evolved a larger brain. This is the brain evolving here across millions of years. And in the meantime, technology also increased. So the complexity of our technology increased, and we have the paleontological evidence for the evolution of a large brain, and we have the archaeological evidence to correlate with the evolution of the large brain, to correlate technological advances to the evolution of a large brain. So a large brain is a good proxy to infer intelligence. And whales do have a very large brain. So absolutely, like in absolute terms, the whale is extremely big. The whale brain is extremely big, and the bigger the whale, the bigger the brain. So here, for example, I'm not completely sure what species this here, but that 9 kilograms of brain for that whale, and here 1.5 kilograms of brain for a human. So of course this is only meaningful when you break it down to body size, because of course you would expect a bigger brain in a bigger animal. So you have to bring it down to body size, and for that we use what is called the encephalization quotient. The encephalization quotient is not just a ratio of brain size to body size, it's in fact a figure that gives you the size of the brain compared to the size of the brain that would be expected for an animal of that body size. So to make it less technical, let me give you some examples. Here, for example, an encephalization quotient of 1 means that the cat here has just enough brain for its body mass. It has just the brain that it needs to coordinate his body. So a cat is not expected to be intelligent. I know there are cat lovers here, but let's be honest, when you point to something, the cat watches your finger. The dog will look at the ball, but the cat will watch the finger. So cats are not the brightest. Unlike dogs, dogs have a 1.2 encephalization quotient, which means they have slightly more brain mass that is expected for a dog. So they have a slightly more brain matter, and that brain matter can be employed for intelligence. That extra brain matter can be employed for intelligence. And if you have less than 1 for encephalization quotient, it means that you are not expected to have brain matter, spare brain matter for intelligence. So now when you look at a human beings classically are around 7 in terms of encephalization quotient. We have 7 times more brain than we should. And whales and dolphins are traditionally somewhere between, well, dolphins in particular are traditionally around 4 or 5. So they are 4 to 5 times more brain than they actually need. And that is extra brain matter, that is extra neurons to build intelligence. So that's why we think that brain size is an important measure of intelligence. And here I put you a picture of the brain of a bottlenose dolphin, so you can see it's not only the size, but it's also the very structure of the brain that's extremely complex. If you compare it to a human being, you see there are more folds and gyri. We call them sulci and gyri. So there are more folds all over the cortex, the neocortex, and it's especially striking when you compare it to another marine mammal, so the manatee, in which there's literally just 2 folds on each side of the brain. So a manatee has a very simple brain compared to a human, and even more compared to a dolphin. So complex brain organization and large brain, that gives you the 2 main arguments to say that, to state that dolphins will be intelligent. And now the question is when and how did that large brain evolve in whales evolution? So last year I presented a whole conference about the evolution of whales and how they originated from quadrupedal animal, quadrupedal herbivorous animal into quadrupedal four-legged carnivorous animals that gradually adapted to life in water to eventually become the whales and dolphins that we know today. So it's a 65 million years long story that Lloyd already summarized, and it's pretty long to tell. So I'm just counting on that tiny animation to sum it up quite quickly, so I don't have to go through this all over again. But the point is, we know that whales evolved from a tiny quadrupedal terrestrial animal. And we've been looking, so paleontologists over the decades have been looking for evolution, for evidence of that brain evolution across whales. And the problem is the brain is a soft tissue feature. It's very squishy. It's not a particularly good material prone to fossilization. Fossilization will turn hard part into rocks, and the soft parts are usually lost. So you barely have any fossil skin, fossil hairs, and fossil organs in particular. The only organs that do fossilize well are your bones. But sometimes miracle happens, and here what you're looking at, these 2 pictures are the picture of the same thing. It's a fossil brain, like a 5 million years old fossil brain of a sperm whale. So this is an actual brain that did fossilize. And this is, as far as I know, the only fossil brain in the world. So how do we know, if there is only one fossil brain in the world, how do we know that humans evolved a large brain? How do we know that anything evolved any brain? Well, we don't look at the brain itself, we actually look at the brain case. So what we call the endocranial cavity. We look at cranial capacity. The brain is contained into a box, and that box, the volume of that box reflects more or less the volume of your brain. So this is exactly what you see it. So we put the fossil whale into a CAT scanner, get it sliced into thousands of X-ray images, And then we put together those X-ray images to create 3D models of the endocranial cavity, the inside of the brain case, which we call endocasts or endocranial cavity. And that's how we can monitor the evolution of brain size. Also, the problem with that is also that you can only monitor brain size. Like all the histology, all the tissue, all those foldings are lost in that process. There's just the brain case left. There's no brain in that endocast. So another reason why I'm focusing a lot on brain size today is not just it's not just because brain size is important to trace the evolution of intelligence. It's also because brain size is pretty much the only thing we can monitor through time, through geological times, that is related to intelligence. So here, this is the result that you get when you look at the evolution of whales and the brain. So here you have brain size, encephalization quotient, so that ratio of brain to body size, from the smallest to the biggest, and here you have time in millions of years. So you're going back in time as you go down. So first it's interesting to look at the top. At the top you have the modern species. So in modern species you have a wide variety of brain size in odontocetes. So odontocetes are the toothed whales, the dolphins, and the other toothed whales. You have a wide variety of size that goes along with a wide variety of anatomy of brains. So you have everything from small brains in the river dolphin from the Ganges, all the way to a super large and complex brain in bottlenose dolphins. So there is a variety of brain size actually in whales. It's not just big brains. There are small and big brains, particularly in the sperm whale. The sperm whale has a very small brain when you bring it back compared to its brain size. And when you trace it back in time, what you see is that diversity narrows down into a bottleneck here of relatively large brain in stem odontocete, in the earliest, most primitive toothed whales. But here, that's the ancestor of all whales, called the archaeocete, that were already presented by Lloyd. So those four-legged whales, the archaeocetes, had a very, very small brain, actually smaller than any modern whales. And here you have that quantum leap from small brain to large brain that happened in primitive toothed whales, and then that diversification that happened much later in time. So around 40 to 30 million years ago, there was a leap in brain size. And that also corresponds to a leap in anatomy. So here, this is the brain of the earliest thing that you can relate to a whale, may I say, because it didn't look like a whale, it looked like a small four-legged herbivore. And here you have the olfactory bulbs, here you have the hemispheres, here you have the cerebellum. And this is a very standard brain for that kind of animal. And then you move up in the stratigraphy, you move up in time, more towards modern days. 35 million years ago, this is the brain of an archaeocete. The hemispheres are beginning to inflate a little bit, and the olfactory bulbs are smaller. And then, after that quantum leap here into large brain, you reach a brain shape and size that corresponds to that of modern whales. So we can definitely say that the modern brain, the modern whale's brain, evolved somewhere in around 35 million years ago, between 40 and 30 million years. And you can see that's not a made-up story. We have all those fossil species here that have been documented, that have been CAT-scanned. It was a long collective work that was initiated in 2005 by a researcher named Laurie Marino from the United States. So this is a huge data set now. This has built up into a huge data set. And recently they even have added to that data set the mysticetes, because we really wanted to know what's happening with mysticetes, with the baleen whales. And the reason is, baleen whales have an absolutely large brain, so large in absolute size, but compared to their huge body size, they have a tiny encephalization quotient, particularly compared to the delphinids, so dolphins and their close relatives. So researchers wanted to look at what's happening in mysticetes, so they documented same thing, many mysticetes. It's the same graph. It's basically the same graph presented in a slightly different way, but encephalization quotient from smaller to larger, and time from younger to older. This is the same for odontocetes, so for toothed whales, the same bottleneck here, the same archaeocetes, and that quantum leap happening right here. So exact same figure, except that they put the baleen whales here. And what's interesting is that baleen whales stayed more, in general, in the smallish range of brain size, but they started diversifying around 5 million years ago, like reaching large brain size here around 5 to 2 million years ago. And what happened there is that suddenly you see that reduction in the encephalization quotient. Like they began to become intelligent and then decided it's not for them. It's exhausting to be intelligent. I'd rather be big and stupid. Stupid and happy. And the reason why we think that happened is because of this animal, not the one here, that animal. That animal is the megalodon, the megatoothed shark, which is an actual species that actually existed. It's a shark with teeth about that size, so about the body mass of a great white. And this shark was a whale killer. It was the top predator of its time. There was no killer whales at that time, and this was the universal whale killer. We know it because we do have tooth marks of this shark on whale bones of that type, which is called the Miocene, so around here. And what happened is that this shark was so ferocious, so thirsty for blood, that it pushed the body size of whales down. Like, whales could not reach a big body size as long as that shark was hunting them. And then suddenly, when it disappeared, body mass skyrocketed. So after 2 million years ago, when that shark disappeared, body mass of whales skyrocketed, and as a consequence, the ratio between brain and body mass shrank. So the relative size of the brain, it's not that the brain became actually smaller, it's just the body that grew actually big, a lot bigger. So this is what we think happened here. Like, when this shark disappeared, the whales stopped. Well, the whales started diversifying in terms of body size, and because the body size increased, then relative brain size became smaller. The brain size became relatively smaller. So two different stories for two different lineages of whales. On the one hand, the dolphins that became increasingly intelligent, and on the other side, the mysticetes that decided last minute to go on the less intelligent side. Doesn't mean, again, that they are not intelligent, but at some point their brain stopped growing. But they still display some evidence of intelligent behavior, and I'm not negating that. So, now why would you evolve a large brain? Because life on Earth began 4 billion years ago, and up until 2 million years ago, everything was small-brained. So having a small brain doesn't prevent you from having a long and happy life. So why would you suddenly, oh, no, I want a large brain? So there are many, and large, not only large, but as I said, complex. Like this is human, this is dolphin. So not only large, but also complex brain. There are many hypotheses, so all of them involve intelligence, of course, like increasing intelligence, particularly increasing social intelligence. There's a strong correlation between social complexity and brain size. So here you see as the social complexity increases, brain size increases. There's the development of echolocation. You see that quantum leap that we've seen between the brain of archaeocytes and the brain of toothed whales. That quantum leap also corresponds to the origin of echolocation, which we can very efficiently trace back because we can study the evolution of the inner ear with CAT scan. So the same technique enables you to follow the evolution of the inner ear. So we know from the inner ear that these whales, the post-quantum leap whale, had echolocation. So there's and echolocation needs a lot of brain power to be processed. That it's a lot of signal that they are sending. Like every clicks, thousands of clicks that they produce every minute, even hundreds per second sometimes. So these clicks, that's a lot of data that they send, and they need to process that information, and they also use them to communicate, which goes back to the social complexity. So, of course, if you ask anybody, and anybody being Homo sapiens, and Homo sapiens likes to correlate brain size and intelligence, as we've seen, if you ask anybody, the reason to evolve a large brain is to become more intelligent. That would be the obvious answer, and that's the currently accepted answer, of course. Now there's my colleague here, Professor Paul Manger from the University of the Witwatersrand, and I'm working together with him on that project that I'm going to present to you now. So my colleague Paul Manger thinks, well, first he doesn't think that dolphins are intelligent, which I disagree with him. But we do agree that there may be more to brain size evolution than just intelligence. And he proposed in a very controversial paper in 2006 that the main driver of brain intelligence, of brain size, would be thermoregulation, so the ability of create body warmth. So you know we are warm-blooded animals. Dolphins are warm-blooded animals too. But it's much more difficult to be warm-blooded in the sea than being warm-blooded on land. Because in the sea you dissipate more heat. So there is a lot more evolutionary constraint on your organs when you live in the sea and when you live on land with regard of that warm-bloodedness. And what's interesting is that the brain plays a key role in warming the blood, and your brain also, because it takes a lot of energy, and when you take energy you create heat. And your brain also needs to be warm to work, because if you have a cold brain you're dead. Observation, scientific observation. The cold brain makes you dead. So, and what's interesting with the brain of a dolphin is you can see it's very round, it's spherical, just like a human brain. It's very spherical, and what Paul Manger has proposed is that just following the simple law of heat dissipation, something that is bigger, like a large brain, for example, an organ that is bigger, will keep its warmth a lot more easier. Like a big coffee mug keeps a lot better, keeps your coffee hot a lot longer than your small espresso cup. You've probably noticed that. Like your small espresso cup, you have to drink it very quickly, otherwise it gets cold in an instant. Especially in winter in Johannesburg. It goes better here. So the larger, the better for body warmth. That's the big idea. And the spherical shape is very important because the sphere is the best ratio between surface and volume. So if you have a convoluted shape, there's a lot of surface that's going to come out, the heat can come out of that convoluted shape very easily. If you have a sphere, you maximize the ratio between surface and volume, which means that the spherical brain keeps its warmth, keep its energy a lot more easily than a brain that is elongated, just like we saw in those primitive whales. And what is even more interesting is that we can trace definitely the evolution of the sphericity of the brain in whales, because we have all those CAT scans that have shown us the exact evolution of the brain and all those data points. And here, we've seen that quantum leap in brain size also corresponded to the origin of a large and spherical brain in toothed whales. And that time, 33 million years ago, is also the time when the circumpolar current was established. So South America broke up from Antarctica right here, and then that current started, and that acted as the air conditioner of planet Earth. Earth hasn't stopped cooling since 33 billion years, to the point that in the Pleistocene you had the very famous ice ages. So we do actually live today in a much cooler environment than it used to be 33 million years ago. I'm not denying global warming, of course, but that global warming is a global warming because we live in the environment naturally should be cold, should be very, very cold. And this is all because Antarctica 33 million years ago. So the environment began cooling down just as whales began grow a big brain. And that correlation, to my colleague Paul Menger, is telling a lot about the evolution of the brain in whales. And he's suggesting, so as I say, he doesn't particularly agree that dolphins are intelligent, but we agree to say that it is possible that intelligence was only a side effect of the evolution of a large brain. The large brain, the large and spherical brain of toothed whales, evolved to maintain the temperature of the brain case, to maintain the temperature of the brain. It evolved to warm up the blood, but by generating more brain matter for thermoregulation, in the end, that large brain had more neurons and so could also generate intelligence. And so what he's suggesting is that, yeah, intelligence was just a passenger on the evolution to adapting to a colder environment. And I think it's very thought-provoking, because when we think now about human evolution, we humans also have a very different way of cooling down our body. We sweat. And there's not a lot of animals that sweat. Most animals pants to cool down their body. So we also have a funny way to thermoregulate, and we also have a funny big brain. So that hypothesis, Paul Menger's hypothesis, may actually have a lot more implications than just on the evolution of whales. It actually could also apply to us. Like, is that very special way that we thermoregulate correlated to the evolution of our very special brain? And he also reminds that there are many other life history traits that are correlated to the evolution of a large brain, such as lifespan. Like most whales live very long. Gestation length, same thing. Most whales have a very long gestation time. Parental care, body size, etc. There are so many things that can influence the evolution of a large brain. So perhaps we should stop focusing just on intelligence. There's probably more to the evolution of brain size than just intelligence, and that's the big idea. That's probably the take-home idea of that talk. And I thank